Hi grade 12s, welcome to lesson 5.4. So this is lesson 5.4. We are going to talk about KW and pH. So yet another K to add to your list. We have lots of K's in the grade 12 chemistry course. Now pH you've already had some experience with. Okay, so when we talk about concentration, we are used to talking about in grade 11 anyways, you would have described concentration for sure as molarity, right? There's other ways we can talk about concentration. There's grams per volume, there's percentage, there's ppm, parts per million, etc., etc. Color we can use as a measure of concentration. But the one we're going to talk about today is actually the pH scale. So when we talk about pH, that generally, we would think about it maybe as things being acidic or basic, right? The pH scale is just another way of describing concentration, but specifically, it's the concentration of the hydronium ion, the H3O+, from the reaction of an acid with water. So an example here, we've got our hydrochloric acid plus water. And remember, the hydrochloric acid is a strong acid, so this is 100%. So this would give us a concentration of that hydronium ion. And so this is how we would use that information to describe the pH of a particular solution. So we've got here, this is just general pH information here. We've got water reacting with itself here. So this is called the autoionization of water. We'll talk more about that in a little bit here. But when water undergoes an autoionization, we end up having the hydronium ion and the hydroxide ion. So make sure language, you know the difference, right? That's hydronium, the hydronium ion, this is the hydroxide ion, okay? Now, in pure water, the concentration of H3O+ is going to be equal to 1 times 10 to the negative 7 moles per liter. The same is true for the hydroxide ion, but because we're talking about pH and that's linked to H3O+, I'm gonna use the H3O+ concentration here. So we've got this chart here. Excuse me, I'll probably have to pause the video, I guess, to copy that down. But when we've got the concentration of H plus and OH minus, now I'm doing this on purpose, okay? So H plus and H3O plus are the same thing, right? Remember that. So you can use these interchangeably, okay? So when H plus is equal to OH minus, this is what we would call a neutral reaction, a neutral solution. So the pH is going to be 7 for that one. And most of us kind of know that. That's in sort of a general science knowledge for a lot of people. And so the concentration of H plus is 1 times 10 to the negative 7. Now, if the H plus is bigger, if that concentration is bigger than the OH minus, we would have an acidic concentrate or acidic solution. So the concentration of the H plus would be more than the 1 times 10 to the negative 7. pH would be, oh my goodness, these are backwards, sorry. Cross these arrows out. That's less. The pH is going to be less than 7 here. And then for a basic solution, the pH is going to be greater than 7 here, and that would be when the H plus concentration is less than 1 times 10 to the negative 7. Sorry, that was a typo there. Now, this is our pH scale, of course, so 7 is right in the middle here. So acidic is our 0 to 7, and then alkaline is just a fancy word for basic. So our bases, our OH minus, this would be in the alkaline region of the 7 to 14. So 7 in the middle, so this would be our pure water here, and then basic solutions are 7 to 14, acidic solutions 0 to 7. Okay? So this is our pH scale here. Now, when we're calculating the pH and H plus concentration, we have two formulas that we're going to use. So copy these down, box them in. You're going to have to memorize these. You wouldn't be given these on a test, for example. So make sure you commit them to memory. So you'll notice here, we're going to use this log button. It's not often that you actually get to use these buttons, right? So make sure you find it on your calculator. I know you probably have used it in pre-calculus class, but we'll use it in chemistry here today. Okay, so we're going to go through an example here. So an antacid solution has an ion concentration of 4.7 times 10 to the negative 11 molar. So what is the pH? So right away, we know the formula, right, for pH. So the pH concentration, or sorry, the pH, the formula is the negative log of the H plus concentration. Now, we know that the ion concentration is this, so that's what you're going to dump into that equation here. So 4.7 times 10 to the negative 11, and you end up with an answer of 10.33. Now, let's first talk about whether that makes sense. Then I'm going to talk about sig figs. So does it make sense that it's a pH of 10? If we look back here, a pH of 10.33, so that puts it right in here. So that means it's a basic solution. So reading the question, it's an antacid solution. So that means this would be like your Pepto-Bismol, that kind of stuff that you would take if you were having like acid reflux or something like that. Or you had an upset stomach, you would want to calm down that acid. So you'd want to neutralize the acid a bit. So it makes sense that the pH will be 10.33 because that's basic. So so if we have a base and an acid, of course, that's a neutralization equation, right? So it makes sense that we have 10.33, so we're good. So now let's talk about sig figs. Now, where the sig figs come from? Yeah, it's interesting. So you look at the question. So if I look at the question, I know that I've got 2 sig figs here, right? So the 4.7, that's where my significant figures is going to come from. Now, the number of sig figs is equal to the number of decimals in your answer. So the 10 doesn't even count for sig figs. It's the number of decimals. So if I had 3 numbers in your sig figs, you would have 3 decimals. If I had 1 sig fig, I'd have 1 decimal, okay? So that's where that comes from. So make sure you know that so you don't lose half marks on that one. Okay, so let's just do the problem in reverse here to show that it works, that everything works okay. So do the problem in reverse. So if the pH is 10.33, calculate the concentration of H+. So looking at our formulas there, we know that the concentration of H+ is equal to 10 raised to the negative pH. So 10 raised to the negative 10.33. So you're going to type that into your calculator, raise it, and just basically I just want you to be sure that you are able to punch everything into your calculator, okay? And you get an answer of 4.7 times 10 to the negative 11 moles per liter, and then your unit for that is going to be concentration. Okay, so it works, everything's good. Make sure you, I don't know, I have a double decimal there. Make sure you know how to type everything into your calculator for this to work. Now, when you do this one, I should have mentioned this before, actually, that negative sign, don't use the subtraction symbol on your calculator, you're gonna use the negative sign, okay? Okay, so there is a shortcut that you can do if the integer is 1, okay? So for example, the H+ concentration is 1 times 10 to the negative 2 molar. The pH is 2 in that case. So when the integer is 1, so when this is 1 straight with no decimals, the exponent is going to be equal to the pH. That's why the pH is 2 there. So you can still do it the long way, but if you want to have a shortcut here, it works fairly well. So if the hydronium ion concentration is 1 times 10 to the negative 6, what is the pH? And so here you would simply have to say the pH is equal to 6 here. And technically it would be 6.0 then because of the sig figs. So that's how you do that. You could also feel free to, of course, dump it into the formula and figure it out that way. Okay. Now we have something called pOH as well. So we've got the pH, we've got pOH. So if the pH is a measure of the H plus concentration. POH is a measure of the hydroxide ion concentration, so of the OH minus. So these are our formulas here. So these two are the same as the pH formulas, but of course using OH minus instead of H plus. But we've got this third formula here. Now, the pH plus the POH is always going to be equal to 14.00. So we can use this information to solve things later on. So just keep that in your back pocket. We're going to come back and use that later on in the unit here. Okay, so find the hydroxide, well, I might use it today actually. Find the hydroxide ion concentration of a solution that has a pH of 2. So, yeah, we are going to use it today. So, looking at this, I know the pH is 2, but I want to find the hydroxide ion concentration. And my formula for that is going to be 10 raised to the negative POH. So I need to find the POH first. Now, if the pH is 2 and the then I can find the POH. Because remember, pH plus POH is going to be equal to 14. So if the pH is 2, this means our POH is going to be 12, okay? So I can put 12 into there now. So the hydroxide ion concentration is going to be 10 raised to negative 12. And you should, once you do that, try it out on your calculator, you get an answer of 1.0 times 10. No, is that right? No, hold on. Let's see. 10 raised to the negative 12. Oh yeah, there we go. Yeah, for sure. Is going to be equal to 1 times 10 to the negative 12. Okay, and molar, sorry. Don't forget that. Gotta have your units. So 1.0 times 10 to the negative 12. Now, technically I didn't even have to do that. I could have used our rule there, but whatever. We'll just dump it into the equation for that. So the hydroxide ion, 1 times 10 to the negative 12. Okay, we're going to talk about the autoionization of water again here. So this is, we've seen this formula before on the other slide. So in pure water, the conductivity is very slight. Now, conductivity is a measure of ions. So what that tells us is that if we don't have very many ions would be, these things here. If we don't have very many of them, that tells us that equilibrium is strongly shifted to the left. So it's really favoring the water molecules. So not very much of it ionizes to the H3O plus and OH minus. Now, we can construct an equilibrium law equation based off of this. So remember, we've got K equals products over reactants. So we can say K equals, and then our products are going to be our H plus times the OH minus over H2O. Now, we do know, though, that the concentration of water it's a liquid, so it's a constant. So that's not going to change. So we can include that in up here. So if we include that, that now becomes part of the constant, which is where we get our KW for. So that's K water. KW then is going to be equal to H plus times OH minus. Now, in pure water, we know the concentration of H plus and OH minus. Each one of these concentrations in pure water is 1 times 10 to the negative 7. And so if we calculate that out, this is going to be 1 times 10 to the negative 14. So 1 times 10 to the negative 14 is what KW is always going to be equal to. Hold on, sorry. So it's always going to be equal to 1 times 10 to the negative 14 for KW. Now, if we add an acid or a base to the solution of water, they will either increase the H plus or the OH minus, and it will cause equilibrium to shift. So, for example, we've got, H3O plus OH minus. Now, if I added a base to this water, that would cause our OH minus concentration to increase, causing a shift to the left, right? So this can happen. It will shift. However, the concentration of H3O plus multiplied by OH minus is always going to be maintained. It is always going to be 1 times 10 to the negative 14, okay? So make a note of that, and this one we're definitely going to use in our next lesson here. We're going to continue on with that. So keep that in your back pocket. You are going to use that for the future. Okay, your assignment today is exercise 20, and I believe, let me just check, I think I gave you guys the answer key already. Yeah, the answer key's on the back, but try it on your own first, of course. Make sure that you know what you're doing. Okay, thanks everyone.